I'm deeply honored to receive the award under Ralph Peck's name. To me, to many of you, Ralph Peck is an indispensable professional icon. And to me, among many of his accomplishments and the personal attribute, the foremost is his personal persistent pursuit on the study of case history. Case history provides trailheads for understanding, analyzing, and solving many challenges in engineering. So today, I'm very pleased to have the opportunity to share with you my journey. It all started 15 years ago. The failure of many natural and engineering slopes under variable saturated conditions originates from changes in hydrological conditions, changes in the water level in rivers, in reservoirs, in oceans, and moisture in atmosphere. Moisture change results in rainfall and snowfall. What you see here is the moisture originated from tropical in Pacific Ocean and move northward toward the land. As moisture moves to the land, the temperature reduces and correspondingly humidity increase and results in rainfall as well as snowfall, depending on the hydrological condition. And here's the satellite picture that you can see that clearly what we call the atmospheric river. The atmospheric river is different in many ways than the river running on the land. It is in the vapor form, other than it is the same with the river running on the land is water, which is the liquid form. Here, you can see that the creative pattern of this atmospheric river, when they hit the land, they're going to cause many of the landslide problems. On the east coast of the United States, we also have a much more dramatic atmospheric moisture condition, what we call the hurricanes. It originates from Caribbean and Atlantic Ocean. It also will have this particular storm in the fall, later summer, early fall, to land on the east coast. When they hit the mountain of Appalachian, particularly in the southern end, it also will cause extreme precipitation. And all this will result in many of the landslides, whether it's engineered slope or natural slope. What you see here is back to the west coast of the El Nino year of 2005. And here is the picture that we took after the particular season, that you see that the scalp, the white scalp, that those are all the landslides due to the precipitation of that particular El Nino year. We know that the atmospheric in the Pacific Ocean operated in a very interesting way. In some year, it is very dry. It's called a La Nina year. In some year, it's very wet. It's called El Nino year. The cycle of the El Nino, La Nina actually somewhat it's unpredictable. Even for today, puzzles many of the atmospheric science. It somewhat come with between 3 years to 7, 8 years. But what's interesting here is you see that the pervasive in those El Nino year in certain part of the west coast. And it actually only change precipitation sometimes by a very few months. And here's the close-up look, a picture of those resulting damage, or at least threaten many of the neighborhood as we expand further into the Mother Nature. So from those landslides, you see that we can ask some of the fundamental as well as the practical questions. So do slope always fail under saturated condition? This is a very important question because up to now, most of our civil engineering design and geotechnical design on the slope is based on saturated condition. So practical question is, can we use the classical slope stability paradigm to predict a rainfall-induced landslide? Theoretically, can we continue use Terzaki's effective stress? As well as, can we use a single factor safety to predict instability for individual slope. So those questions generate many of the challenges for us. My journey to study slope started from about 20 years ago when I joined the Colorado School of Mines. As you know that my colleague Von Griffiths gave a talk this morning, and he is actually the one that actually introduced me to the challenging problem of slope stability. And we have he had a picture of a donkey with a bag of dynamite. So you know, a donkey with a dynamite, how powerful it is. And most of the time in Colorado, we destroy the slope. We explore on the hillside to find the energy, oil, minerals. So after I joined the Colorado School of Mines, I was fortunate to have a colleague also at the U.S. Geological Survey. Some of you know that the U.S. Geological Survey National Information Center is located in Golden. In fact, it's located on our campus. And in early 2000, the leader of the U.S. Geological Survey's landslide team, Rex Baum, come to talk to me about the landslide problem they have. And most of the time, up to that time, the slope stability monitoring they have is all under saturated, monitor anything under saturated condition, in other words, anything below water table. On the land surface, we do some of the deformation measurement, but not within the distance between the ground surface to groundwater table. So at the time that they asked me what we can do for the soil under partially saturated condition, because based on some of the monitoring sites they have in the West Coast, the failure appear to occur under partially saturated condition. Not sure, not 100% sure scientifically. So at the time, because of my experience with USGS prior to my joining the Colorado School of Mines, working on the nuclear waste underground storage. So I have a fortune to be able to expose to some of the unsaturated soil condition, how we can characterize stress and soil moisture. So I said, well, maybe we should put some stress pole there to see how we can analyze that. So that was the beginning of the trailhead. Then PhD student at the University of Colorado, Jonathan Gott, is the one that actually put those sensors into the slope. Now to look at the problem, I will show you how that particular problem in the Pacific Northwest is important. And here's the videotape somebody took from the parking garage, monitoring the slight movement of slope failure slowly, and as you see that. It will take a little bit while, but just maybe 30 seconds. Be patient. It's very valuable to record those events. It's the real case history that you can go back to look at that. So where's the problem? If you look at the Pacific Northwest, particularly near Seattle, we have a very distinguished geological feature called Pigeon Sound. And along the Pigeon Sound, on the one side, west side is the sound, the other side is the hill slope. And those hill slope is very steep. Some will still puzzle some engineer or scientist is that because most of them are sandy soil. But how come the slope can stay at 45 degrees on average? And also it's very thick. And most of the landslide results from the rainfall, heavy rainfall. And some years, actually, it's become a perennial event. Every year, there's some kind of damage there. So it's a big concern. And also the shallow landslide in this case involve many of the, as I said, the soils. This is under the glacier soils. As you see, can imagine that 30,000, 40,000 years ago, one time was about a kilometer or two of the ice on top of those glacial materials. So it's heavily over consolidated. And we put those monitoring stations, if you come back here, is on the hillside, two of the borehole, particular that when Jonathan Gott was a PhD student, they put the two borehole there, all the way in Vader zone. One is in the upslope, the one is in the downslope. And also we put a rain gauge nearby there to monitor that. That was back to 2002. And since 2002, nothing happened. 2003, nothing happened. 2004, nothing happened. But we got some kind of sense of the hydrological behavior. But 2005 is the year, as I mentioned, is El Nino year. And something happened there. I just plot out the three histograms. One is the precipitation. As you see, only plot between September 2005 to January 2006, all the way to the point where our monitoring site failed. And there's also two landslides nearby, also about 30 to 50 yards, also failed. Between the time of these 3 to 4 months, the precipitation cumulative is about 500 millimeters. And you can see that what we measure is the soil moisture in terms of suction at the different depth, all the way from the shallow to relatively deep, as well as the soil suction. And I will talk a little bit more about soil suction and soil moisture, because that's one of the important things that we need to understand very well, particularly under partial saturated condition. So it's clear from those observations that up to the failure, that the soil is under unsaturated condition, which is not 100% saturated. It's also clear that suction is still maintained even after the failure. So that's one of the first scientific document that we have to sure to say that the failure of the slope is under partially saturated condition. Now imagine that what could happen is that when the rain comes down, it's going to change the water table, particularly even in a very rapid fashion. And it may cause failure. So the question we can ask ourselves is how we can deal with the failure of the hill slope. And most of the time we use effective stress. We use Takazaki's effective stress under saturated condition, which means that we only capture the skeleton stress under the fully saturated condition. So two related issues that we have to address. One is unsaturated fluid flow and how the stress changes. Can we think about that and conceptualize and put into the framework that we already have used for the saturated soil mechanics and slope stability analysis? So two questions here. How to better understand soil water retention? So soil water retention, basically how the soil moisture and suction, as I show you that, they interact with each other. The second is how to formulate a unified effective stress framework. Some of you may be aware that the unsaturated soil is one of the, I would say, the very active research, not only in the geotechnical arena, but also in other related disciplines, such as hydrology and soil science and agriculture. So the unified effective stress framework has been there for saturated. Can we do that for under partially saturated condition? That is the question that I have been thinking about for a while. Let's come back to the soil-water interaction. So what is the soil-water interaction? People have heard a lot about soil suction, soil moisture. Here what I show you basically is the relation of the soil water and the matrix potential. The matrix potential is a much more general term than what we call the matrix suction, because it reflects the potential of the water. For a given soil, if for a given degree of saturation or moisture, the soil and the water is going to reach thermodynamic energy equilibrium at one point, which is on this curve. Now, if you change the soil moisture, that equilibrium point is going to change. The equilibrium is under the energy between the soil and the water and the air. So that's what we call the soil-water characteristic curve. Why bother talk about this soil-water characteristic curve? Because I think for the last 40 years, even for soil science, even today, we're still under debate. What is the origin of the soil suction? In general, there are two mechanisms for soil suction. If the suction is relatively lower, which means close to the water table condition or the saturated condition, in a few hundred kPa, most of the soil water is in the capillary retention form. As I show here, it's a little minuscule. You can use your eyeball to look at that. But as the soil gets drier and drier or suction gets higher and higher, you actually transition to another regime that we call the absorption. Absorption could be further divided due to the particle surface absorption or due to the exchangeable cation hydration if you have a clay material. And that will result in very different behavior. But it's still somewhat vague when the soil is going to transition from the capillary to absorption. Further, it goes to the transition between the particle surface and the cation hydration. And the study of the capillary is the focus of the last 40 years. And people have been using the definition of the pressure differences between the air pressure and the water pressure as a matrix suction. But in the transition regime, in fact, the people find that it is because the van der Waals attraction start to take over the physical chemical force. So the question here is, can we still use the definition of a matrix suction or pore water pressure to continue use from saturated to unsaturated? The answer is we don't know. But it's clear as the suction goes to higher and higher, all the water will be tightly bounded by the cation. Under that regime, we cannot use the pressure concept because the pressure concept becomes local. If you look at the pressure near the particle surface or cation surface, the pressure could be positive. But the potential is very lower because the soil, or dry soil in general, they are in a much lower potential than the water that we have, free water. So this is one of the research area, even for soil water retention, for soil science, soil physics. And recently we have some breakthrough. And we can actually separate the water retention between the capillary and the absorption. This makes huge differences because many of the things, particular effects I will talk about next slide, is based on the concept so far. Some of you probably hear that after Tazaki, Bischoff, professor at the Imperial College, had the formula for effective stress for unsaturated soil. Those are intrinsically actually only consider capillarity. So if we will be able to separate the water retention mechanism specifically for capillary water and hydration water, we will be able to understand what is the role that toward the effective stress. And that's exactly we have been working in the last 15 years. So here is an illustration about what happened under partially saturated condition. If you look at from the mechanical perspective, you can lump the stress distributed based on these two absorption and the capillary mechanism. The total stress is there, everybody knows that. It is mainly due to external stress and gravity. Then we have what we call the physical chemical force, van der Waals attraction, double layer revulsion. That is due to the absorption nature. Then we have the negative pore water pressure, where the suction is relatively lower, typically lower than a few hundred kPa. And that is where the capillary region is, capillary water is most active. Of course, when you have a capillary minuscule, you have the surface tension, which is in addition to the negative pore water pressure, the pressure lower than atmospheric. But if we do that conceptualization, we can actually retain the Tazaki's effective stress to the same form. As you see here, the total stress and the suction stress. So I call in the term with my former student, now colleague, Bill Lyko, called the suction stress. The suction stress, basically, you can conceptualize into two components. One is due to the absorption. The other one is due to the capillary. The one due to the absorption is still something that we don't understand very well. In some way, as I said, because it depends on how we can separate the water between capillary and absorption. But the one for capillary, actually, by now, it's quite clear. It has a lot to do with how much area those pressure is going to acting on when soil under partial saturated condition. But lumped together, this is a characteristic for each different soil because their mineralogy, their pore size are very different. Therefore, this is the constitutive relation between the soil water content and the effective stress. So that is the term we call suction stress. With suction stress, we can actually unify the effects in a consistent way. So imagine that the unification I'm talking about here is when we have a soil here on the showing here is the soil water retention for three very distinct soil: sandy soil, silty soil, and the clayey soil. You see that the sandy soil does not retain a lot of absorption water because they are in the lower suction regime. It's all capillary water. But the clay has a lot of absorption water because the suction is very high. The unification comes from that we'll be able to advance to the knowledge that we can actually characterize suction stress using the soil water retention parameters. Because fundamentally, they are happening in these two distinct mechanisms. So if we understand how those water redistribute in capillary form and the absorption form, we can actually characterize the stress. So the capillary stress I have here, as you see that, they only need two parameters, what I call the air entry pressure and the pore size distribution. And both of them actually, you can use identical parameter to characterize your soil water retention curve. So the problem becomes much more clear and simple. We can use the effective stress framework. We don't need to change the shear strength failure criteria. So that is what we have. Now let's look at the data that we have to see how we can interpret that. And I show you that this event of this episode from September 2005 to January 2006, after several of the episodes of rainfall, you can see that clearly the suction is increased depending on the depth, as well as the suction is decreased and the more saturation is increased, as well as the suction is decreased. And if you use the framework, what we have learned to unify effective stress, you simply times the moisture content or saturation with the suction, that you get the capillary part of suction stress. And you can put that one into the infinity slope model. And I generate this, the figure with the factor of safety for infinity slope model. Here, all we need to do is to change the pore water pressure by suction stress. And you can clearly see that by the time the persistent rainfall is in December, January 2006, the failure occurred because the factor of safety below or equal to about 1 at a depth of 1.5 to 2.5. I have to say that this is one of my highlights of my career because in February 2006, Rex Baum, my colleague at the USGS, called me. He said, "Ning, your theory works, and here's how." And he showed me this original diagram that can basically put everything together using the effective stress, same kind of failure, cohesion, friction angle we have been using for saturate. But instead of using pore pressure, using suction stress can precisely predict about the timing where that particular landslide is going to occur, as well as the depth. So that gives us a lot of confidence. In the decade after that, we start to pursue this framework. We start to see how we can continue define and of the framework to different sides. So we do a few things. One is we are expanding for the different area where we think that is most vulnerable for landslide or slopes instability, in some cases engineer slope. So we have 2008 in Portland, Oregon. Then 2009, we installed the largest scale in a valley of Ilial Forest in the Oregon Coast Range. And 2010, we expand to San Francisco Bay Area. And we actually, by now, we have 8 stations around the peninsula and the East Bay to fully monitor under different kind of conditions. And back to the Colorado, in 2011, we also installed on I-70. There's a landslide near the Continental Divide, Colorado is very unique in terms of precipitation because the snowfall, as you know, that as early as September, as late as May. In the high elevation, the snow basically will not melt until in the spring, sometimes in April or something. And then it will melt within a week because the temperature rise above the freezing point. And the I-70, there's one section near the Continental Divide, the Eisenhower Tunnel, is the ongoing landslide in the last 25 years. Every year when the snow melts, the highway start to slide, a couple inches. And then will stop in the later summer. It will come back again. So this provides a great opportunity for us to install that one. And in 2013, we had the opportunity to put our station for the first time in 3 locations in western North Carolina, where the landslide can occur under different kind of hurricane condition. I'll come back to that size later on. The framework we have tried to do, meanwhile, we are monitoring all these stations. We also try to establish a framework, put it into the context of modeling. So what we do is we integrate 3 components. One is the geomorphology. By now, we have information from remote sensing satellites, all those. We can know very well on the surface, at least, about the geological topographic information. We can also use the hydrological framework to understand how the water is distributed in hill slope, as well as the slope stability we can conduct. If we look at the objective, what we try to do for slope stability, we always try to capture what is the driving force, what is the resistant force, because that is the one that will provide the rationale to see whether the slope is stable or not. And we start with the geomorphology, the best information we can have today. We use the hydrological information, which including put it into the computer simulation to understand how the water is going to distribute under partial saturated condition. And in the traditional geomechanics, we can also use a framework, just like my colleague Von Griffiths this morning, using the finite element, using the linear, elasto, plasto framework to understand how the slope is going to change under different stress conditions. Now, what's missing is the 3 components which I think we have explored in the last 15 years. One is we established the direct coupling between hydrology, unsaturated hydrology, sometimes I call variable saturated hydrology, and geomechanics. The second is we unify the effective stress, as I showed you earlier, unify means between hydrology and the soil mechanics in terms of how we deal with effective stress. We also try to explore the paradigm. Again, my colleague Von Griffiths this morning talked about the reduced strength, reduce other method. Instead of assuming one slope, one factor safety, here we explore the field of factor safety because we know the stress distribution and we know enough information about hydrology. We can develop a field of factor safety. That gives us a much more precise way to assess where is the vulnerable area and where the failure is going to initiate. If I want to summarize the new framework in comparison with the classical one, in the classical framework, what we try to do is to use the shear strength parameter. If you're interested in saturated seepage, we will need to know what is the porosity, what is the hydraulic conductivity. In the framework we try to establish, we try to minimize, while retaining the effective stress framework, we try to minimize the parameter. In this case, I summarize only 3 parameters. One is inverse of air entry value, which actually is the capillary fringe that actually you can physically, you drill a borehole, you make observation, you can actually measure that. Of course, we can measure in the lab. One is a pore size distribution. The other one is called residual moisture content, which basically is a simple version of the absorption water, how much for a given soil it is. So the new framework, in reference to the classical framework, it added 3 important constituent relations: soil water retention curve, sometimes called soil water characteristic curve, hydraulic conductivity function because it's unsaturated, and the suction stress characteristic curve. And the important thing about that is we have shown that all three curves actually correlate. In other words, we use the same set of parameters to analyze that. And the other thing is we try to look at the factor safety. How can we predict that in a precise way? I will use a reference of the classical one to illustrate how we do the factor safety field. In the classical, we all know that we have to assume some kind of geometry of the failure surface, or geometry. We have to make an assumption what we call the liquid limit equilibrium analysis, which says that either the slope will fail or not fail. It all will fail concurrently, simultaneously. So those assumptions actually prevent us to be more accurately to see where the failure is going to occur, as well as how it's going to evolve. So there are some limitations about that. And what we come up with is a very simple method to use to define the factor safety, what I call the local factor safety. Because we know that each point, by now we have a very advanced computational method, we will know that what is the total stress, what is the effective stress. In this case, if you use a suction stress, that we can generalize both the saturated and unsaturated condition. We know the current state of the stress. We will also know the material property, which is from classical. In this case, I just use a straight line of Moore-Coulomb criterion. We know the current state, where is the most vulnerable point, which I call the Coulomb stress, that has been used in geology, in predicted earthquake. And what is the potential, which is an extension of the Coulomb stress. And you can define how safe that particular point is using the parameter that we have already defined, friction angle cohesion, as well as the effective stress. And this is particularly useful for under the rainfall condition, because we don't change the gravity too much. Sure, we change a little bit about moisture weight, but mostly the total stress remain about same. We don't change the external loading. So the state of stress basically move leftward, as I use here. So this method, you can basically calculate the field of safety. Let me illustrate through two cases. One is using the vertical cut slope. And this slope is either dry or saturated. And the slope, we can use a different classical method to calculate what is the failure surface as well as the factor safety. As you see from top to bottom, the slope becomes stronger and stronger because the number we call cohesion increase results in the M parameter increase. And most of the slope here in the first and the second is safe. It's unsafe. And then you see the third and the fourth one, most method predicted safe. Now if you do a stress analysis, finite element analysis, and if you look at the contour of this local factor safety, you will see clearly where is the likelihood of the failure. And for the slope, I will point out too that is the third one, C, that in the traditional method, we will basically predict all the slope factor safety is greater than 1. While in reality, if you calculate the stress, you will see that the red area, it's actually reached the failure. And the last slope is very clearly illustrated. Even though the slope factor safety using traditional method can reach a 1.5, the 1.5 is some kind of magic number that we have used in slope stability. Your slope actually start to initially fail. And this will see the shape of the failure in many of the reality, as well as actually you can use this technique. I will use a C again as an illustration to see if we have a progressively fail, what happened. So this is after like 3 iterations. The first one failed, we take away just manually. We can do much more robustly now, but this is just to illustrate it. And then recalculate the stress distribution, and so on and so forth. By the time we do the 4th iteration, we can get this slope, which actually is very much mimic to many of the slope, natural slope we observe, with the characteristic concave in the top of the slope and the total slope, as well as the linear in the middle of the slope. Another example that I can illustrate to show you is the shallow landslide. So this particular 30 degree of slope, as you see by the traditional method, all of them, the factor safety is greater than 1.
But if you do a stress analysis, in this case just total stress, because it's dry or completely saturated, and you'll see that the first slope actually already start to fill in the very shallow way, the pattern. And the second slope, even though it's safe, 1.25, the area where there's a weak, you can also identify. The third slope, you have a two weak zone. One is shallow, one is deep. So imagine that if you have a precipitation, depend on the intensity of the precipitation. If it's very rapidly, you can actually cause a shallow landslide. If it's kind of a slow trigger down, they actually can penetrate the seepage downward to much deep, cause much deep landslide. So slope failure, particularly under rainfall condition, the geometry, it's very different than most of the classical method that we can predict. So let me use a few case studies to illustrate this framework. The first one, I go back to Colorado, and this is a case that actually is not on the Eisenhower Tunnel. It is on the state highway that where I drive every day or I take a bus every day. And it's a man-made slope. It's kind of cut slope, but it's relatively flat and a compact soil. And after 2 years of the construction, the slope fell. Again, in the wintertime, the snow, the fall accumulate. And in the springtime, within 5 days, as I show here, the snow just melt. So we can look at the analysis to see how this occur for this type of landslide. So what I show you here is just a few of moisture content, the change in effective stress we call suction stress, and the factor of safety field. As you see from beginning, the shallow as well as deep has some weak zone. Because the snow melt and turn into water and infiltrate so fast, you can see that as it progresses, 2 days, we can start to see the failure surface emerge near the slope surface. And you can do that simulation to basically repeat it of what happened in the field condition. So as you see that. The second example I want to use is to go to East Coast in Western Carolina and go back all the way to reconnaissance the case back to 2004. Some of you may recall. In 2004, there are 2 sequential hurricanes hit the East Coast in September, separated by 9 days. And the cost of that particular hurricane events, Hurricane Francis and Hurricane Ivan, is over $30 billion of loss. And that particular is very interesting because that year, many of the landslides in western North Carolina occurred. So here is during that particular 2 weeks or so, the precipitation globally. And I circulate out where's the area where we have a landslide observation there. Total precipitation within that week or two, it's actually here, it's more than a feet or so. Now if you look at the hurricane, how they rainfall precipitation, the first one, Francis, swept through the Western Carolina, and then the second one is almost identical trajectory. It hit that 9 days later. So this is a very good opportunity for us to monitor and to reconnaissance. And so we did a simulation for the failure slope where the North Carolina Department of Natural Resources had a detailed documentation about the before and after, how it happens for the particular field slope. They maintain the regular monitoring. So what I show you here is the pressure field, the water content, the change in effective stress, and the local factor safety, how they evolve. I put in the middle, which is the failure surface. If you see red, that is what happened for the failure. So the first event of Hurricane Francis swept through, and you can actually see some local failure near the surface of the slope. And then after 9 days, the second one, the Ivan, come, and you can see much more pervasive connection of the failure surface. So we use the framework to be able to reconnaissance that. So that's very encouraging. So let me come back to the last case I want to show, which is where my journey starts, back to Seattle. I show you that using an infinite slope model. Here, I'm going to show you using the numerical model to be able to use the unified effective stress framework. And here again, I will show you how the soil water content is going to evolve, how the pressure, suction stress, which is effective stress again, and the local factor safety. And this is the beginning of those episodes start from September. As you see, the precipitation episodes start to get more intense. Each of them come with a week or two and then stop, and then for a while, and then start again. And as you see that, as this El Nino winter storm gradually precipitate there, and we start to see the failure. And eventually, it caused the landslide that we observed that one. I was very glad that when my colleague, Jonathan Gore, and I went to the site, and we did a detailed mapping, and the failure surface actually, to a great extent, very much coincide with what we predicted in this case. So I'd like to summarize my talk today. Slope failure can occur under unsaturated, or we call variable saturated conditions. And it can be analyzed by using one-way unified effective stress, what I call a one-way couple, hydrological and the mechanical, retaining the same framework we have done for saturated condition. And the key here, first to start with the soil-water equilibrium. To understand how the moisture distributed as well as the suction distributed, we will need to solve Richard's equation, which is become a classical story and equations for the hydrology. We also can use a unified effective stress. In this case, it's a suction stress that provides a rigorous linkage between hydrological variable and the mechanical variable that we are concerned. So no need to define new failure envelope or failure parameter, using the same one that we have been used to analyze that. And we use a local factor safety to fine-tune the predictability of the likelihood where the failure is going to initiate and ultimately how they evolve. And the case study actually for me provided incredible journey to understand, and we are continue to do so. So in concluding, I would like to paraphrase Rolf Peck's remark on the importance of good engineering. Engineering is indeed a noble sport, and the legacy of good engineers is to create better environment for mankind. Thank you.